In this tutorial, I will explain what FPort is and a short refresher what a JSON object is. I will also explain what payload formatters are and show you several JavaScript payload formatters examples. This presentation can be found at this location. All my LoRaWAN tutorials and presentations can be found at this location. In this video, when v2 is mentioned, v2 refers to the Things Network. And when v3 is mentioned, v3 refers to the Things Tech Community Edition. This is to keep this video as short as possible. In tutorial 17, I have discussed the LoRa packet format. The LoRa packet comprises of three elements: preamble, header, which is optional, and a payload. And this is the payload cyclic redundancy check. Here is a spectrogram of a LoRa packet. This part is the preamble, and starting from here is the header and part of the payload. Let me see if I can detect LoRa signals in my area using this RTL-SDR dongle. I'm not going to use this antenna which came along with this device. Instead, I'm using this sleeve dipole antenna, which was discussed in tutorial 33. The RTL-SDR dongle attached to my MacBook. If you want to know more about the RTL-SDR dongle I am using, go to YouTube and search for Mobilefish RTL-SDR and you will see this video which I have created. Start the Cubic SDR application. Select this option, press Start. Set this frequency range between 867.1 and 868.5 MHz. That is the LoRa frequency range in Europe. Drag your mouse, and this must be 868. 867. 867.1 is here. So let's zoom out. So 867.1 is over here and 868.5 is over here. Let's zoom out further. Yeah, that's correct. 867.1 and 868.5 megahertz. All right. So select FM. Can click somewhere here, doesn't matter. Oh. You can hide the top window. You can hide this window. So let's set it here. And this scroll bar, set it to 400 lines per second. Here is a LoRa signal. And here is another LoRa signal. This image is taken from the LoRaWAN specification version 1.0.2. The specification can be found at this location. This represents the LoRa packet format. Again, here's the preamble. This is the payload header, payload itself, and the cyclic redundancy check. Let's zoom into phi payload. Phi payload is phi payload, and this is phi payload. All LoRa uplink and downlink messages carry a phi payload, starting with a MAC header, followed by a MAC payload, and ending with a message integrity code. Let's zoom into MAC payload. MAC payload is this MAC payload, which is the same as this. Make payload contains a frame header, followed by an optional port field called FPort and an optional frame payload field. FPort means frame port. If the frame payload field, this field, is not empty, the port field must be present. If present, an FPort value of 0 indicates that the frame payload contains MAC commands only. Our encrypted sensor data is in this field. According to the LoRaWAN specification, FPort values 1 to 223 are application specific. FPort value 224 is dedicated to LoRaWAN MAC layer test protocol, and FPort values 225 to 255 are reserved for future standardized application extensions. But in the technical recommendation, FIOTA Process Summary Technical Recommendation TR002 version 1.0.0 regarding firmware update over the air on top of the LoRaWAN protocol, FPorts 225 and 200, 201, 202 and 203 are listed for specific usage. This table can be found at this PDF file. Combining the LoRaWAN specification and the FIOTA Process Summary Technical Recommendation, users should only use the following ports: FPort 1 to 223, except value 200, 201, 202 and 203. FPort is 1 byte in size. Allowed values are 1 to 223, except FPorts 200, 201, 202 and 203. This byte is always sent, even if you use it or not. Hackers can read this value, but if they change this value, the package is dropped by the gateway because of the message integrity code, that is this code. Your encrypted sensor data is stored in this field. If a data frame carries a payload, frame payload must be encrypted before the message integrity code is calculated. The frame payload is encrypted with the network session key if FPort is 0, otherwise it is encrypted with the application session key. But you can ignore the above mentioned information because it is not relevant for this tutorial. This is my self-built end device. It measures the temperature and humidity. My end device uses this Arduino sketch. This sketch uses the MCCI LoRaWAN LMIC library in my Arduino IDE version 1.8.10. The library can be found at this location. In the sketch, change this function to change the FPort value. In this example, I have changed the FPort value to 1. This is the Arduino sketch uploaded to my end device. And this is my FPort value. If you use the MCCI LoRaWAN LMIC library, more sketch examples can be found at this location. When I set the FPort value to 1 in my Arduino sketch, FPort value 1 is shown here. If I set FPort value to 2, FPort value 2 is shown here. If I set my FPort value to 0 in my Arduino sketch, no sensor data is received. When I set FPort value is 11 in my Arduino sketch, FPort value 11 is shown in my console. FPort value 223 is the highest number I can set, and as you can see over here, FPort value 223 is shown. With my REC72444C LoRaWAN gateway, and this gateway uses the Raspberry Pi 4, I'm able to intercept the FPort value. More information about this gateway, see tutorial 51. To monitor UDP messages sent between the REC72444C and the V3 network, install the TCP dump application. So first access the REC72444C, upgrade the Raspberry Pi packages by entering this command, and install TCP dump by entering this command. Start TCP dump by entering this command. With the TCP dump application, you can monitor UDP messages sent from gateway to LoRaWAN network server and the other way around. The messages which are sent from gateway to LoRaWAN network server has this received package name. If you see this, copy the data field. More information about UDP messages, see tutorial 29. I have demonstrated this before. There is an online tool available which can decode the LoRaWAN 1.0.x packet. That is this online decoder. This online tool uses the LoRa radio packet decoder created by Anthony Kirby. The source code can be found at this GitHub page. Please note, Anthony Kirby is not the owner of this online tool. Use the online tool for educational, demonstration, or test purposes. Never enter your production secret network session key or app session key. From the TCP dump, get the base64 encoded data. This is the online LoRaWAN packet decoder. I've pasted the base64 encoded data in this field and pressed the decode button. As you can see, I've not entered the network session key or the app session key. And this is the output. And here is the FPort value. That is 10 decimal. And this is hexadecimal. Let's log into my rack 7244C. I've already upgraded the Raspberry Pi packages and installed TCP dump. Enter this command to start TCP dump. Copy this information. This is the JSON message I just copied. Receive package. This is the message transmitted by my end device. I know this because of this low RSSI value. My end device is near my gateway. Copy this data. Go to this LoRaWAN packet decoder and enter the base64 encoded data and press the decode button. And this is the FPort value. There are LoRaWAN end devices where FPorts cannot be changed. These devices have fixed FPort values. There are LoRaWAN end devices where FPorts can be changed programmatically, for example in an Arduino sketch, or with add commands. There are LoRaWAN end devices where FPorts can only be changed by modifying, compiling, and uploading the new firmware to the end device. If you want to know if you can change your LoRaWAN end device FPort value, check your end device manual. It is recommended that you use the FPort because this byte is always sent. You might as well use it. Every byte not transmitted improves the end device battery life. But be careful of the kind of information the FPort value represents. Hackers can use this information for criminal activities. I will give you a silly example, but it will get my point across. So do not use FPort if it contains information which can be useful to criminals. This represents a wildlife park. Park rangers are researching this bear's behavior. This bear is unique. It is 3 times its normal size, so it's a very large bear. And the rangers are monitoring how often this bear visits the lake, the feeding area, and a waste dump. These are motion sensors which are placed near entrances. These are entrances to the lake, and these are entrances to the feeding area, and these are the entrances to the waste dump. FPort 1 refers to the lake, FPort 2 refers to the feeding area, and FPort 3 refers to the waste dump. By the way, here is the ranger's gateway. Let's assume on a mountain nearby this wildlife park, the criminal has placed its gateway here, so it can receive the sensor data. Let's assume the criminal knows which area, this lake, feeding area, and waste dump, each FPort value represents. By monitoring the FPort value, the criminal will know in which area the bear is located. The criminal does not know exactly where the bear is located, but it has a general idea where the bear is located. So near the lake, or near the feeding area, or near the waste dump. So the criminal can sell the bear's location to illegal hunters. In this particular example, it is not recommended to use the FPort to represent a certain area. Here is another example where using the FPort value is very useful. So this is a potato farm, and these are sensors measuring temperature and soil moisture. FPort 1 refers to field 1, FPort 2 refers to field 2, etc. The FPort value is not interesting to hackers. There is no monetary gain if someone knows the FPort values. JSON stands for JavaScript Object Notation, and JSON is a syntax for storing and exchanging data. Here is an example of a JSON object. The JSON object starts and ends with curly brackets, here and here. Data consists of key value pairs separated by commas. These are key value pairs and separated by commas. The key, that's this key, must be wrapped in double quotes. Double quotes. Key and value are separated by a colon. The value, these are values, can be a number, number 2 and number 12.44, a string, a boolean, an array, another JSON object, or the value null. This is a JavaScript object. In JavaScript objects, the keys are not required to be wrapped in double quotes. There are other differences, but I will not discuss these in this tutorial. To create this sensor JavaScript object, first you create an empty JavaScript object and just add the keywords device, and assign the value. To assign an array, first create an empty array and assign separate values to this array, and assign the array to the JavaScript object key, in this case temperature. To create this JavaScript object, create an empty JavaScript object, assign the value to the JavaScript object key. Payload formatters allow you to process data going to and from end devices. When a binary payload is sent from end device to LoRaWAN network, meaning an uplink, the data can be converted using, for example, a JavaScript payload formatter. The data can be converted to human-readable data. So in this example, binary data is sent from end device to gateway and from gateway to LoRaWAN network server. And here is the payload formatter, which converts this binary data to a human-readable data. When a message is sent from the LoRaWAN network to the end device, meaning downlink, the message can be converted using, for example, a JavaScript payload formatter. The message can be converted from human-readable data to binary data. The message can be converted from human-readable data to binary data, which is then sent to the gateway, and the gateway broadcasts this data, which is received by this end device. The payload formatters used in the v2 console cannot be copied and pasted directly in the v3 console. The v2 and v3 payload formatters are different. For example, the function names and the function parameters are different. In this tutorial, I will only focus on the payload formatters used in the v3 console. This is the decoded payload formatter used in the v2 console, and this is the corresponding decode uplink payload formatter used in the v3 console. So the function names are different, but also the parameters are different. This payload formatter requires a JSON object as its input. In the v3 console, several payload formatters can be used. JavaScript payload formatters. More information can be found at this location. Cayenne low-power payload formatters, which can be found at this location. And device-specific payload formatters. Device manufacturers may have payload formatters designed to work with their devices. More information can be found at this location. The v3 payload formatters can be applied to an entire application or to a specific end device. Here is my application, and one device, this device, is assigned to this application. When I enter my payload formatter here, the payload formatter will be applied to the entire application. And if I enter my payload formatter here, this payload formatter will only be applied to this specific device. I will call this application level, and I will call this device level. Depending on the selected payload formatter, meaning entire application or end device specific, you will see 5 or 6 formatter type options. If you enter the payload formatter for the entire application, you will see these 5 formatter type options. And if you enter a payload formatter for an end device, you will see these 6 formatter type options. This is the one extra. Use application payload formatter. On the application level, these are the formatter type options as discussed earlier. When selecting none, any enter payload formatter is removed and replaced with the default payload formatter. On the device level, these are the formatter type options as discussed earlier. When both device and application payload formatter are specified, the device payload formatter is used. But when you select the option Use Application Payload Formatter, the application payload formatter is used. It is recommended to use the application payload formatters and only use the device payload formatters when there is a need. If your application has 2 or more LoRaWAN end devices and they all transmit the same kind of sensor data, of course, you should specify the payload formatter on the application level. The payload formatter tester is only available on the device level and not on the application level. Go to Applications, select my application, Payload Formatter on the application level, select Uplink, select JavaScript, no payload tester available. Let's go to the end device. This is my end device assigned to this application. Select Payload Formatters. And as you can see, a payload formatter tester is available. When no payload formatter is used, you will only see the received binary payload. In the event details, you will only see the binary payload. The payload is not formatted. And when a payload formatter is used, besides the binary payload, you will also see the payload which is formatted. In the event details, you will see the formatted payload. Let's first look at the uplink JavaScript payload formatter. A sensor transmits this binary data using this FPort. The LoRaWAN stack referring to this software creates a JSON object called input with the following key value pairs: FPort key with the value 8, this 8, and the bytes key with this array. Hex value 01 is converted to decimal value 1, and hex value 0A is converted to decimal value 10. When you specify the decode uplink payload formatter, this input JSON is already available with these values. And this is how you access the input object values. In this example, a JavaScript data object is created. Instead of data, I could give it any name. The returned JavaScript object has a key called data, and this object with these values is displayed in the console. In the decode uplink function, the returned object can have the following keys: the data key, which is a JavaScript object as value, a warnings key, and the value is an array of warning strings, and an errors key with a value which is an array of error strings. To recap, the decode uplink function has only one function parameter called input, which is a JSON object. The JSON object is automatically created and always contains 2 key value pairs. The FPort contains the FPort value. When binary data is transmitted, for example 096007, this data is automatically converted to an array of separate bytes each in its decimal representation. So 09 becomes 9 decimal, 60 hex value becomes 96 decimal, and hex value 07 becomes 7 decimal. And this array is assigned to the bytes key in the JSON object. The payload formatter outputs a JavaScript object. The JavaScript object can be empty or contains a data key with a JavaScript object as its value, an errors key with an array of error messages as its value, or a warnings key with an array of warning messages as its value. This is the payload formatter tester. You enter hex values in this field and you enter the FPort value. The hex values are automatically converted into an array of decimal values, as you can see over here. And the FPort value you enter here is the value of this FPort key. This becomes the input JSON object, which is used by the decode uplink payload formatter. If a warning is present in warnings, the warning is displayed. The payload is valid and the message will not be dropped. If an error is present in errors, the error is displayed, but the message will be dropped. As you can see, there's no empty object displayed here. In the previous example, an empty object is displayed. Here's another example. If you enter this byte payload, it creates this input JSON object, and this input JSON object is used by this decode uplink payload formatter. This payload formatter outputs this object. And the same applies for these byte payload inputs. Next, I will explain the downlink JavaScript payload formatter. This is the encode downlink function, and this is the decode downlink function. The encode downlink and the decode downlink functions are inverses of each other, which I will explain in a moment. The encode downlink function is required, but the decode downlink function is optional. You start with a JSON payload and an FPort. The LoRaWAN stack automatically creates this input object with this data key and FPort key. This JSON object is this payload, and this FPort value is this FPort value. The encode downlink function has access to this input object, and the encode downlink function returns this JavaScript object with the keys bytes and FPort. In this example, this byte and this FPort value are transmitted to the end device. When a decode downlink function is specified, it uses this input object and returns this JavaScript object with a data key. In this example, the data key contains this payload information. In the encode downlink function, it uses this payload as input, and in the decode downlink function, it returns this JSON as output. This is the input and this is the output, so they are inverses of each other. To recap, the user creates this JSON payload and this FPort value. With this information, an input object is created. The encode downlink function has access to this input object. The return JavaScript object can have the following keys: bytes, FPort, warnings, and errors. In this example, the returned object is a JavaScript object. Using this example, it returns this JavaScript object. The JavaScript object is converted to a JSON input object, as you can see over here. The decode downlink function returns a JavaScript object which can have the following keys: data, warnings, and errors. If you specify a downlink formatter, the encode downlink function is required, as mentioned earlier, but not the decode downlink function. The decode downlink formats the binary data bytes into human-readable data, just like the decode uplink function. Here's another example. The encode downlink function has only one function parameter, input, which is a JSON object. The user creates a JSON object. This object is assigned to the data key of the input JSON object. This is done automatically. The Encode Downlink has access to the input object. In this example, the returned object looks like this. This is the Payload Formatter tester. You enter your JSON payload here. This payload is used as the value of the data key, and the FPort has this value. This input JSON object is automatically generated, and the Encode Downlink function can access this input JSON object. In this example, an error is generated. If an error is present in errors, as you can see over here, the error is displayed, as you can see over here. The payload is invalid and the message will be dropped. As you can see, no message is displayed. In this example, a warning is displayed. If a warning is present in warnings, the warning is displayed, as you can see over here. The payload is valid and the message will not be dropped, as you can see over here. If you enter an empty JSON payload, as you can see over here, this empty payload is assigned to this data key. Here is another example. Try to figure out yourself if you can get this result. This is the same example, but now using the Payload Formatter tester. Instead of 10, you will see the hex value 0A. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.